So, welcome back. Don't forget to like, comment, and subscribe. Today we have a theorem now, and so the theorem is, firstly it says that this set is algebraic in some sense, and moreover, if we look at the proof of the theorem, we see that we can find generators for the ideal. Namely, we take some generating set of the kernel, actually like some set of integer vectors which span the rational kernel is enough. So we could have done the whole business with with the matrix A having coefficients in Q instead of in Z, which would be slightly more sort of relevant maybe to statistical things. But I want to do two examples to see, because last week we talked about these examples a tiny bit. So Sullivan, he described these ideals and he gives us some finite generating sets. And the question was like, where do these generating sets come from and how do you find them? So he has a general theorem saying the ideal is generated by binomials of this form. And then he writes down finitely many which actually generate it. And the question is, how do you find them? And so from the theorem we can do that, but let's just do a couple of examples. So his first example was the twisted cubic. So for some reason we call it the twisted cubic, which is some sort of geometric thing. But all we have to do to describe what's going on here is to write down the matrix. So 0, 1, 2, 3, 3, 2, 1, 0, so I'm thinking there's a linear function from z or q to the 4 z squared. Yep. And so the kernel is spanned by 1, minus 2, 1, 0, and 2, minus 3, 0, 1. You do some sort of Gaussian elimination, like, I was preparing my first year lectures and these familiar things. And so these give us equations. So I'm going to take this set to be my B, these two things. So I'm going to get the equations x1, x2 to the minus 2, x3 equals 1. So this is like, if this is B1 and B2, that's very good B. So this is FB1, is this equation, or minus 1, sorry. FB2 is x1 squared times x2 to the minus 3 times x4 equals 1. Well, again, we have these negative exponents, so let's just push them on the other side. So we can find that the ideal that we want is generated by x1, x3 minus x2 squared, and x1 squared, x4 minus x2 cubed. Okay. So if you look in the notes, Sullivan gives us another generator, which is x1, x4 minus x2, x3. So so Sullivan gives us this generator. So the subset of R4, which these two ideals cut out, won't be the same, but they'll have the same intersection with the probability simplex. Because these ideals will only give us different zero sets away from this sort of locus where all the variables are equal to 0. Because if you allow yourselves to invert the xi's, then this is in the ideal generated by these. How do we write this? Forget. I did this and then I forgot it.
So which ring are you now writing down ideals?
So these are all ideals of the polynomial ring in x1 to x4.
And if you add the inverses, then they come with the same ideal.
Yeah, so sorry, let me be more precise. So I'm going to call IS is I plus Sullivan's guy. Okay, and then we have V of I and V of IS. So these are both subsets of R to the 4. And they're not equal, but the sort of the exercise for the reader is that V of I intersect R star to the 4 equals V of IS intersect R star to the 4. In particular, V of I intersect with the interior of the simplex is V of IS intersect with the interior of the simplex. So they're different ideals, but the only difference is about what happens in this sort of boundary, and we don't care about that. As far as I can, like for the statement of the theorem, we don't mind about that. Okay, so this was a people who sort of.
Do you happen to know if both ideals are radical? Or is that?
No, I don't know if my idea is
Yeah,
radical.
right.
But I also don't.
You don't care. Yeah, indeed.
But this is the same as the question I had. So this theorem
Actually, it
is
is
about.
radical. I'm sorry. Oh no, sorry. I retract. I don't know. Sorry, everyone. Please go on.
So, but I guess I already know the answer, but to make sure I do, this theorem and everything you've done so far is about the zero sets, right?
Yeah.
So we don't have any results yet about whether the ideal of certain sets is what we want it to be, or given by something.
So I know that, but I know that this ideal, so the ideal generated by the FBs in R join x1 to the plus and minus 1, this ideal is radical.
Oh, okay.
Yeah.
I don't know if when we take this just sort of naively extend it to the whole, like naively clear denominators, I don't know if it stays radical. But in some sense, sort of the part that intersects the probability simplex is reduced.
Yeah.
And I also, like, my philosophy is that I don't really mind whether things are radical anyway. So I feel that this is sort of a...
No, but you want to give the best equations in the set that you like. So you have to give the radical ideal after you invert these xi's. Right?
But it's not always true that the radical ideal has simpler generators than the
No,
ideal.
but somebody gives you a set, and you give an ideal for that set. Well, so then logically you're asked to give the ideal of all function generators for the ideal of all functions. I mean,
I sort of disagree. Like, so I mean, I see what you, like, that would be a very natural question, like ask for the ideal of all functions radically.
Yeah.
But very often the reality is that this set comes, there's some construction which gives this set. In this case, it was the image of this sort of rational line. And to me, often these constructions will give you a natural ideal, and it may or may not be radical. Like if you took the image of something non-reduced, then it would be non-reduced. And I'm not interested in the image of the radical at that point. So the radical of the thing.
yeah. Well, but for the probabilists, I think they only take sets that they don't look at schemes. They have sets, and you ask what is give me generators for the ideal of functions vanishing in some set.
But I guess my problem is I'm not sure why we asked this. Because we haven't really seen a sort of an example which is interesting to statisticians, as far as I'm aware yet.
Yeah.
And so I don't know if we do see such an example. I don't know whether we'll care about the ideal, whether we find the radical of the ideal, or just somehow.
Well, maybe you want to know something about. You want to see if a function. What do the functions vanishing on that set look like, right? I think that's a natural question.
Yeah.
And if you can generate them somehow, that's a good thing.
Yeah. I guess what I would want to do is I want to save this discussion until after we have more interesting applications,
Okay.
and we can see really what happens. I mean, you may well be right, but I mean, it's not a right or wrong thing. It's more a philosophy thing. But I'd rather see
But
the.
you want to know about the set, and nice alternative ways to characterize it, and properties of it.
So
Yeah.
So it can
I'm not
often.
interested in all polynomials which happen to be zero on the set.
It could, for
Wait
example,
until you see the difference.
but it could, for example, it might, for example, be that you have some idea with very few generators, and then the corresponding radical ideal needs many more generators. This can
Yeah.
happen. And so actually, if what you want to do is a very quick way to check if a point is in your set, you'd rather have the fewer generators of what happens to be a non-radical ideal. So I think, yeah, as you say, it really depends on the application.
Okay.
Okay, so the next example is hopefully slightly more interesting for the sort of statistical application. So this is this complete independence thing. And this is very embarrassing. I've forgotten exactly why this gets called that. So I'm sorry. I mean, I was listening during your talk, but I did not follow everything. But I'll write down a matrix, and then maybe someone can remind us why we call this complete independence thing. So A, it's a 6 by 8 matrix. I will actually write the thing because it's important for the calculation we'll do in a second. You're noticing some sort of symmetry here. This is familiar from your talk.
Yeah, it's complete independence because there are three, you can write the probability as 3 random variables and they are mutually independent.
Okay.
You can see that.
3 variables each taking 3 values.
Yes, they each of them take, 2 values.
No, each
So
take
3 variables
So 3 times
and
2
they
is
take
6.
2 values.
3 binary variables.
3 variables each taking 2 values, and they're
So that means
paired
you have
mutually.
Yeah.
so there are 8 probabilities, and there are lots and lots of independencies.
Yes. Okay. So let's write down the ideal, so this gives us some subset of our interior of our simplex, and let's write down the ideal for that thing in the same way. So what we do is we row reduce. So you can do this by hand, or you can ask Wolfram Alpha to do it for you. Fortunately, all the other rows are easier. They get more and more zeros every time, as we should expect. And then the next 2 rows are just zeros. Okay, so this means that our null space, so what are they? 1, -1, -1, 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. That doesn't seem good. I think I want to put another 0 here. And there's 2 to go. 1, 0, -1, 0, -1, 0, 1, 0, and 2, -1, -1, 0, -1, 0, 0, 1. Phew. Okay, so let's take this to be our set B. And then again, we can write down our corresponding things. Well, so I mean, I will skip writing the f's. I'll just write the f primes because I think the theorem denominators we can all manage. So our ideal generated by x1, x4 minus x2, x3, x1, x6 minus x2, x5, x1, x7 minus x3, x5, and x1 squared, because it's a terribly written 2. We've got a 2 here. x1 squared times x8, x2, x3, x5. Okay, so our ideal is generated by 4 things. Here they are. So in the notes, in Sullivan's notes, again, so he makes this ideal which is sort of maybe different on the boundary but the same on the interior of the simplex. He computes it using like Grosvenor basis algorithms in singular, and it has 9 generators. So if we're only interested in the interior of the simplex, then this we can do by hand and gives us like fewer than half as many generators, so it seems better.
Sorry, I asked this question again, I guess, or similar, but now that's the question again. So is it true, did you say that these generators in the ring where you have inverted the variables is radical?
Yeah.
But presumably because he gets some more stuff, maybe in the ring without inverting the variables, it's not radical?
I also, that could well be.
And do his things perhaps, but at least those, okay.
That makes sense. I'm slightly confused because
Or maybe you get even some extra components.
I think
Yeah.
that's actually
that
the
probably
case.
happens. And it also may also not be radical, and I have extra components. Yeah. So it goes. So the last thing that I want to do, which will be very quick, is I want to give a more general. So I guess we have this thing in the book where we have we prove lemmas in algebra, but they only we prove lemmas in algebra, and then we have definitions in statistics, and we somehow want to make them match up. And it's a bit awkward because the real numbers are not algebraically closed, and that makes life inconvenient. And so what I want to do is I want to give an analogous sort of result coming from algebra, which looks very much like the theorem that we had before, but it's actually a different. I mean, it's not. I don't think neither one implies the other. So root ring version. Really, I mentioned this partly because, so there are 2 reasons why I bothered to do this. One is because people asked me last week, is there some sort of more conceptual thing underlying what Sullivan's proposition does? And to me, this is sort of the answer from an algebra-geometry point of view. The other reason, what was the other reason for doing this? There was another reason. Oh, so actually, I proved the group rings version first. So I was looking at Sullivan's sort of algebra proof. I proved the group ring version, and then I try to deduce the real points version that we saw earlier, and then I realized that A, I couldn't, and B, it was super easy if you just took log and did linear algebra. So this was something that I went through on the way to the thing that we ended up with. So a definition. So if G is an abelian group, and lambda any ring, then we have this thing called the group ring, which is lambda square brackets G, and the elements, so as a set, it's just Holmes from G to lambda, just maps of sets from G to lambda, and the multiplication, so that makes it into
finite support functions. Is your group finite?
no.
Yeah.
Thank you. And the multiplication is a little bit weird, so if I have, say, f and f prime from G to lambda, then I define f times f prime of some little element little g is the sum over g I, g j. Like different ways of, like things, sort of ways of making g as product of two things. Okay, so here we have a very fancy and general definition. This thing is naturally a lambda module, like it hasn't, like you can sort of multiply by lambda, for example. So examples which maybe make it slightly more reasonable, if we take k adjoin z, this is just a fancy way of writing k adjoin x inverse. So the idea is that the element 0 in z corresponds to 1 in this ring, 1 in k corresponds to x, 2 corresponds to x squared, 3 corresponds to x cubed, minus 1 corresponds to x, or minus 1. So you can think of these elements of the group as being sort of exponents of your variable in some sense. And similarly, k adjoin, say, z to the r is the ring that we saw before. And so
Yeah, can I bother you and try to find out again what you mean by Holmes G lambda?
So what I mean is just maps of sets. So for every, there's maps of sets from G to lambda, but with finite support.
Maps
so
from G to lambda?
Yeah. So with finite support, as in they take the value 0 for all but finitely many elements of G. So for example, here I require that my polynomials, otherwise because here I require my polynomials have only finitely many non-zero coefficients. So that's why this finite support condition comes from.
Yeah, maybe you're more used to something else, right? If you have a Lie group, you could take functions, real functions with compact support, and then convolute. Convolution as multiplication.
And that's basically the same.
That's it. Yeah.
Nice. I hadn't thought of it like that. That's really cool.
So people do this, right?
Okay, and so I'm not going to go through proving things because I imagine this is not so, it's sort of like a bit mysterious to the statisticians, but I will try to at least state the lemma. So if I have phi from G to H, a group homomorphism, this induces a map of lambda G, lambda algebras, which I'm going to call lambda phi from lambda G to lambda of H. I guess which in the notation I've written there, it's just, yeah, apply, no, it's a bit ugly. Well, I guess the nicest way to think of this, think of these things like polynomials with coefficients in G, and then I apply the function to those things, and then I get some element of this gadget. And so the exercise for the algebraic geometers, if they feel like doing it, which I don't massively recommend, but the kernel of lambda G is generated as a sub lambda module of lambda adjoin G by the set of EG minus G, where G runs over the kernel of phi. So the kernel of phi is potentially some sort of infinite thing. So EG minus G, so in other words, so what I should write is the function from G to lambda, which takes the value 1 at the unit of the group and the value minus 1 at the element G. So this is more carefully written as and everything else goes to 0. And then a sort of easy corollary of this, well, this is maybe just another part, and the next bit says that then kernel of lambda, sorry, that should be phi, of course, look at this on the map. Kernel of lambda phi is generated as a lambda g module, as a lambda g ideal, if you like, by, oh, sorry, so let B generate kernel of phi. So B is any generating set for the kernel as an abelian group. Then this kernel is generated as a lambda g module by the set of E, G minus G as G runs over B. So as a lambda module, you need a generator for every element of the kernel of phi. But as an ideal, you only need a generator for like some basis of the kernel of phi, and that's sort of where these finite generating sets come from, essentially. Like, if you have, so the map phi A that we wrote down came from a map of group rings, and so the kernel is generated as a k module by these things, and as an ideal by these guys, which is where the finite set comes from. So, okay, that's everything. We are free.
Is there questions for the speaker?
You can start.